Okay, so let's continue from where we left off last time. So we were doing wave equation, PDE on a disk. And the formula was, the equation was UTT equals to C squared of U. And then, because it's a circular disk, there are actually two directions. On the boundary, it should be 0. We're thinking of something like a drum. When you beat a drum, the boundary would be fixed, right? Whereas internally, it's going to vibrate. So in the circular direction, you have that U R pi and t is equal to U of R negative pi and t. U, and if you differentiate in the theta direction, you also have this. And then we were saying that A theta t is set to be 0, so that the boundary condition is 0. This is the radial part, this is the angular part where it should be periodic. And then finally, initially somebody has to beat the drum, so there should be some initial conditions. So U of R theta 0 should be a function of R and theta, whereas U of UT of R theta 0 should be given as G of R theta. Then we actually had done this problem considerably, and we're almost at the end of the result. So what we did was we tried to say U R theta t is equal to R of R, theta of theta, t of t. And when you apply this to theta, we realize that theta must be, theta of theta should be C1 cosine n theta plus C2 sine n theta. Maybe I used A and B. Did I use A and B? Or did I use C1, C2? Can't remember. Alright, well anyways, this is what I did. And then we spent considerable amount of time thinking about R of R, because that's actually the hardest part. It gives you the Bessel function. And the formula for this is J of Jn. So that's the Bessel function of order n. And I have Jnk. Actually, I should divide by A. Jnk divided by A times R. Okay. And that's what I had, where J and K is the kth positive 0 of J and X. Okay. And then T of T, and I was checking my last lecture's video, and I realized I forgot something here. It should be, could be, I'll use A and B. A cosine J and K over A, and then I just wrote T, but that's missing. So if you still have last week's notes, please put a C there. I just forgot to, when I was solving for T, I forgot this C squared somewhere. So there should have been a C there. Plus B sine J and K over A CT. Okay, so that's what I got. And that's a pretty good result, because now we know that all the non-trivial solutions of this wave PDE on a disk that satisfies the periodicity condition in the angle and the boundary condition 0, so the ones that satisfy this much, are this times this times this, or this times this times this, or this times this times this, or this times this. Those are the 4 types you can make out of all these, right? Do you agree? Right? You just think about all the possible products of these, and then those are the 4. So here is what we end up with. Actually, there was actually a part where I wasn't too clear. So there was a part where I wasn't too clear, which is that you could also have n as 0, and in that case, theta will just be a constant. And this is something that we've done when we did the Laplace equation on the disk as well. So that does exist. And then when that happens, when n is 0, this is still a non-trivial solution, and you get another non-trivial solution for r as well, which is J0. N would be 0, and certainly Bessel's function of order 0 does exist as well. And then because J0 does exist, all these J0k, J01, all of these make sense as well, so everything makes sense. Oh, by the way, I should actually point out that, note, the Bessel function is j of n of x is equal to summation of n equals to, not n, k equals to 0 to infinity of, is it 1 at the top? I think it's 1 at the top. It's a k factorial, n plus k factorial, and you have x over 2 to the power of n plus 2k. I hope I'm right. Is that right? Can somebody check? I think that's right. Definitely the x's skip one order, so that if the first non-zero term is x squared, then it only has x squared, x fourth, x sixth, so on and so on. If the first one is an odd power, then it skips by 2. So if it's 3, then x3, x to the 5th, and x to the 7th. That's how it works. Can somebody double check me? Am I right? Yeah. That's right? Okay, thank you. All right. I don't want to make a mistake. Okay. All right, so this is what we have, and therefore, combining everything, we have the general solution u r theta t as this gigantic sum, where n could go from 0 to infinity, and then you also have k, right? You have n and k, and the reason you have double sum is because this is a two-dimensional wave equation, right? So if you remember, when we did the one-dimensional wave equation for a string vibration, we had tt and just uxx, and that one had a single sum. Okay. Now here it's a double sum because we have one dimension higher. Okay. So that's going to be starting from k equals to 1 through infinity. And the reason k starts from 1 is just simply because it's the way we define j and k is the kth positive 0 of j and x. Yes?
I think j and x should have a negative 1 to add on top.
Ah, thank you. That's right. Okay, then it's right. Okay, thank you. Yeah. All right. So, yeah, of course, we're missing that one. Okay. All right, so it starts from 1, and then you have, now you combine all the terms and see, it's a gigantic sum, so I'm going to put a big parenthesis here. just big parenthesis. And I'm just going to say A n k. Did I use A for something else? I have A without index, but I guess it's okay. So A n k. J n k over A r theta t. That'll be the order I'll go. Okay, so cosine n theta, and then cosine j n k over A c t plus b n k j n k over A r, and this time I'm going to choose the sign, so sine n theta, and then still cosine j n k over A c t, and c n k j n k over A r, cosine n theta again, but this time it's sine j n k over A c t plus d n k j n k over A r sine n theta cosine, no, sine j n k over A c t. And we close the parentheses. Okay, so you have this huge summation. And now let's find out what these A n k, B n k, C n k, D n k should be. And these are not determined because we haven't applied the initial conditions yet. If we apply the initial conditions, then we know what those are. Okay? So let's try to find out first what happens if you plug in t equals to 0. So if you plug in t equals to 0, then you get fr theta. So you get fr theta equals to u r theta 0. And what happens is that immediately, because t is 0, these are 1s, whereas this one will be 0. Right? So these go away. So what that tells us is that you can only figure out the A n k's and B n k from fr theta. Okay? Now, what does that mean? Then what's going to determine C n k and D n k? Can you answer that? What is going to determine C n k and D n k? G of r theta, right? Because this is differentiation by t, and if you take this and differentiate by t, the cosines will turn into sines, whereas sines are going to turn into cosines. And therefore, when you plug in 0 afterwards, those are going to go away, and instead you're going to have a formula for C n k and D n k. All right, so that's certainly possible. And because other than having these extra things coming out from the chain rule, it's the same kind of story here. I will only write the formulas for fr theta, and then maybe give you a homework for finding out the formula for gr theta, because it's almost the same thing. Okay. All right. So let's try that. Now we have summation of n equals to 0 through infinity, sigma k equals to 1 through infinity, A n k j n k over A r, and then we have cosine n theta plus B n k j. Oh, in that case, I guess I should have factored the j and k out. I was dumb. All right, but it's too late. I'll write it. Okay. So that's what we have. And what what that tells us is the following. If for a moment, if we forget that this is a function of r and theta, just fix the r. Am I missing something? Is this okay? All right. So cosine 0 becomes 1, cosine 0 becomes 1, sine 0 becomes 0, sine 0 becomes 0. So these don't appear. Only these become 1, and that's what I end up with. Okay? All right. So if we forget for a moment that this is a equality between functions of r and theta, just let's say we fix r. For a fixed value of r, what do you see? This right side is what? It looks like something. Just consider this as a constant and this as a constant, right? So what does it look like? It looks like something times cosine n theta, right? Plus something times sine n theta.
Yes.
What's that? Expressing it. What would that be? What is this called? Expressing a function as sum of these. What's that called? Fourier series, right? Yeah. So we just do the Fourier series. Okay? Except that it's a bit more involved here. So what's happening is that actually in front of cosine n theta, it's not just this, it's actually this much that's in front of cosine n theta. Is that right? This of this is in front of cosine n theta. So here's what we have. We have that summation of k equals to 1 through infinity of a and k, j and k over ar is equal to, because this is really like a n, right? It's like a n. Oh, I just realized something. For the formula for the Fourier series, you have a separate one for a0 and an, right? So I should really write something for a0 first. So make this as 0. I should write this as 0, 0, 0. That corresponds to a0. And the formula for a0, where theta goes from negative pi to pi, would be the following. It's 1 over 2 pi, integral from negative pi to pi, of fr theta dr. Oh, no. Oh, yeah, it's dr. That's just that. Right? Okay. And then the next one would be k equals to 1 through infinity of a n k, j n k over a r equals to 1 over pi, negative pi to pi, of f r theta times cosine of n theta. Oh, sorry, this shouldn't be r, it should be theta. D theta. And then finally, for the bn's, it should be bnk, jn k over ar should equal to 1 over pi, integral from negative pi to pi, of fr theta sine n theta d theta. Okay? So for a moment we forget that these are functions of r, and you just treat this as a constant, and then you apply the usual formula for the Fourier series, right? It's 1 over 2l, integral from negative L to L, d theta, 1 over L, negative L to L, the function times cosine n pi over L theta, d theta. So these are the formulas that we know of. Okay? And now think about both sides as function of r. Okay? So you can see that if you integrate this, theta will go away because it's a definite integral, and theta will be just used for integration. And at the end of the day, these values are going to go into the theta, so theta will be gone. But you're still going to have r there. Right? That's also a function of r. So you have some function of r, and you're trying to express it as sum of functions of r. Same thing here, you have some function of r, and you're trying to express it as a sum of function of r. Some function of r, you're trying to express it as a function of r. Okay? Now, so how do you do that? Well, I guess I can erase everything. Now, this relies on something that we haven't covered yet, so I promised to cover this after showing this. It's something called the free Bessel series. And it's just like this idea where you can express any function as sums of sines and cosines. That's what these formulas are saying, right? You can express any function as sums of cosine and sines. Here now the other thing is saying that you can express any function of r as sum of these functions. That's called, so instead of expanding a function or expressing a function as a sum of infinite series of sine or cosines, now what you're trying to do is you're trying to express a function as sum of Bessel functions. That's crazy, right? It sounds crazy, but it does work. Okay? So in fact, what happens is that there's an orthogonality relation. So using orthogonality relation that if you have integral from 0 to a of Bessel function of order n at gamma, no, not gamma, j n k over a of r times jn, and instead of k, let me use m over ar, dr is equal, you have to multiply by r for some reason, okay? So you multiply by r, it's equal to 0. And I will prove this today. My goal is to prove this actually after, before the end of today's class, hopefully, okay? And then, so this is true for k not equals to m. And then if k is equal to m, you know that it's not going to be 0 because it's something squared, and r is also positive, so this entire thing is positive inside the interval 0 to a, so you get some positive value in that case. So the idea is like this. So let's for a moment just denote this function as capital Fr. And let's see what we can do with it. So we're imagining, so imagine that indeed capital Fr is equal to some E1 J N1, no, N J N1 over AR plus E2 JN2 over AR, something like this, okay? Imagine something like that happens. And the question is, how am I going to get these coefficients? How can we find that? So the way we do it is, we take fr, multiply by r, and also jn k over a r dr from 0 to a. Then if I plug this entire thing in here, what's going to happen? You can expand it so that you have this times this, this times this, this times this, this times this, and then you have like infinite integrals, right? So let's just say that k is something like 5. Okay. Now, if that's the case, what's the integral of this one with this times r? What would you get? What would this times r integrated from 0 to a would give you? The answer is right in front of you. What is it? So let's imagine that you plug this entire thing. I'm too lazy to write it down because it's just too much. But if this goes, so if you expand this so that you get this times r integrated from 0 to a, what would you get? Let's say k is 5. So you have jn5 and jn1. These two things are multiplied with r, and you get integration from 0 to a. What would you get? Why?
Orthogonality.
Because of this, right?
Yes.
If these two numbers are different, you get 0, right? So everything will be 0 except just one thing. Which one? When k is equal to the same thing, right? So what's going to happen is that when you have this one, at some place you're going to have ek j of n, j and k over a r, right? And when this gets multiplied to this, that's a square. Square functions are never 0. It's never negative. It's always positive. R is positive from 0 to a, so when you integrate, you're going to get a positive value. Okay? That will be the only positive number, and the end result will be like this. You're going to get, ek is some number, it's a constant. So you can bring this outside, and the end result is that you get 0 to a of r times j and k over a r squared. So this entire thing squared dr. Okay? And therefore, you can divide this, right? And get ek equal to integral of 0 to a of r fr jn k over a r dr divided by integral from 0 to a of r times j and k over a r squared dr. If you do this, then you have these coefficients, okay? So that the end result is that once you do this, then you have these sums. So I'll give you a little bit of time to write the notes because it's just like crazy. But now let's see how that's going to help us here. So what I'm trying to do is I take both sides and integrate from 0 to a with respect to r times this times j0 of j0k. Then that's going to give me a0k. That's how this formula is applied. Okay. I guess I'm being a bit lazy today, not trying to write too much, but it's just too much to write. So what I'm trying to say is that if I take each of these identities and integrate from 0 to a, r times this, then on the left side, I'm going to be isolating the a0k, whereas on the right side, I'm going to have a double integral. Okay? Same thing here. A and k will be the outcome on the left side, and you're going to end up with the double integral. And then, by the way, this side will still have this denominator multiplied, so you have to divide out that thing on the right side. So here's the result if you actually do that. So you're going to get that a 0k is equal to 1 over 2 pi of 0 to a, negative pi to pi, of r times f r theta d theta dr, divided by, you have to divide by this one, so, oh, sorry, I forgot this one, sorry. I have to multiply by j0, j0k over a, that doesn't move right, j0k r d theta dr. I'm so used to dr d theta, so maybe I should be changing this. Okay, well, it doesn't matter. So you have 0 to a of r times jn k over a r squared dr. Okay. So that's going to be our a0k. And that's a start. And everything else is pretty much the same pattern, so let me just erase this. That's a start because we have to find a and k and b and k, and then I found part of a and k. So let's write down a and k now. A and k would be, what is it? We're taking an integral of this side. So it's 1 over pi, integral from 0 to a, negative pi to pi, r times fr theta times cosine n theta times jn k over ar d theta dr, divided by integral from 0 to a of r times jn k over ar squared dr. And now b and k, 1 over pi, 0 to a, negative pi to pi, r fr theta, cosine n theta, jn, oh, that's not cosine, that's sine, jn k over ar d theta dr, divided by the same thing, 0 to a, r, jn k over ar squared dr. Okay? And I've almost solved it. Okay, so I'm going to leave you as a homework to figure out what's the formula for C and K and D and K. Right? Now notice that these are very abstract. I'm not actually giving you the explicit question. Like if I were to give fr theta as something like r times theta or something like that. Yeah. And then can you calculate that? That would be a question to do, right? Then you would have to actually calculate these integrals, which, because you have the Bessel functions, you can only do it numerically. So you know how to calculate integrals numerically? I mean, I can't do it. I can't ask you on the exam, but you can certainly make the computers calculate numerical integration, right? What are some ways to do numerical integration? You may have learned a little bit in Calc 2. Do you know like the upper sum or lower sum, right sum, left sum, trapezoidal? That's actually the most important one. What's the last one?
Oh, you mean the partition thing?
Yeah.
Oh.
How do you do it? There's a Simpsons, right? Simpsons rule. Now that would apply here, but when it comes to double integral, now you have to pick points on the disk. So it's harder. But you can do it. You can write computer programs to calculate the top and bottom, and that's going to give you the solutions. Right? Okay. So once you find these, and then you know these, and then you know you can find these as well in the same manner, and then that's the solution. Right? Okay. Now I know that several of you might not feel so satisfied after seeing the solution because we were used to actually getting the values explicitly, and this is nowhere near what we were doing so far. So let me give you a different perspective on these solutions. So do you have any questions on this? Is this okay? Can I erase some? Okay, I'm going to erase this right side. Oh, I shouldn't be erasing the side. Okay, I'll just erase this much. And I want to write down the wave equation for, what's the wave equation? For a string with both ends tied. So this one's UTT equals to C squared U XX, and then U X0 is 0, U0T is 0, 0T is 0, ULT is 0, so then it's a length L string, and then the endpoints are tied, and you have U X0 as some function, and UT X0 as some function. Now, to make things slightly easier, if I just ignore this one, and so this one will also count where G of R theta is 0, and then the C and D you're not going to see. Let's compare this with this. Now this solution will look like the following. UXT would look like, now it's not a double sum, it's a single sum. And it's going to be n equals to 1 through infinity of, you're going to have an sine n pi over Lx, and then cosine n pi over LCT. Okay. Now, the reason you have this solution is because, first of all, when x is 0, sine 0 is 0, and when x is L, sine L is 0, so these will make these two satisfy automatically. Right? Whereas this one, when you plug in time t equal to 0, gives you some non-zero value, whereas when you differentiate this and plug in 0, you get the derivative as 0. So actually the time t of t gives you one of this one, and the one will be the sine one, and the sine one would disappear if this is 0. Okay? So this is a vibrating string, whereas this is a vibrating drum head. So if you have a drum that's circular, and you hit it, and it starts vibrating, it's going to give you that. Okay. All right. So now, what I want to point out from this comparison is that on this string, these become all the possible ways that this string can vibrate. Right? So when n is 1, that's the lowest order, you get sine of 1 pi over Lx. And what that does is that you have 0 to L, you have this as the shape. Okay? That's the shape of this function from 0 to L. And then the amplitude is an times cosine n pi L over ct, so this cosine function makes it vibrate, go up and down. Okay? So you're going to see that it vibrates like, and goes back and forth like that. Okay? But this is not the only solution of this wave equation. It's a sum of this one plus another wave. The next wave will be this one with 2. And what it does, it'll be like this. Right? And then this, again, the amplitude will change, so it's going to be vibrating like that. So it's going to go like this, right? Okay. Plus, so you kind of see what's going on, right? What will be the third one? You're going to have this, right? 3 things.
Yes.
So the middle one goes like this, and then the other one goes like this, and then so on and so on.
Yes.
Okay. And what this means is that when you actually have a vibrating string, your ears are actually a very good Fourier analysis machine. Okay? You can hear different pitches. If you hear a high pitch, you recognize it as a high pitch. If you hear a low pitch, you recognize it as a low pitch, right? So that when you hear this, you're actually hearing multiple pitches given at the same time. You just think of it as a single sound, but it's actually sum of a bunch of different sounds. Okay? And that's why I brought my guitar today, not to like impress you with anything, but just to give you this demonstration. So, so with my guitar, here's a. You hear this as a guitar sound, but if you do, so what did I just do?
2 sounds.
So it was vibrating, and I touched the exact middle, and you start hearing a pitch that's 1 octave higher, right? So why did that happen? Well, what happened was that I put my finger right here, and then it immediately kills all the odd vibrations. So the ones that are here, here, and the next ones, the ones that where the middle ones vibrate, they get immediately killed. But you still hear this sound and this sound and this sound. All the other ones you can hear. Okay? Yeah. That's what's happening. Now, let me also try this one. What happened now? Oh, I should be doing this one first. Da-da. What's that?
It's like a longer something.
So, do you know the intervals in music? It's like if this is the bass first note, this is like the dun 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 dun. What's that? Huh?
The third.
No, this is fifth interval. So what's happening is actually it's not the fifth. It's actually the 5 plus 8. So is that how you say it? I'm not so sure. But what it really is happening is that I'm putting my finger right here. Right. And by the way, this is an actual technique in guitar. So you might have a piece where you do something like okay. Something like this, right? It's you hear something like it sounds pretty, but it sounds more like a bell sound, something like that, yeah. So, yeah. So that's called the harmonics, and the ideas are like putting your finger in certain places so that the lower modes get killed and you only hear the higher modes. Okay? And the way that sound is structured is that if this is the base frequency, then this will be the twice of the base frequency, and this will be 3 times the base frequency. And all this is true because of this function right here. If you have n equals to 1 and 2 and 3, you can see that it's all multiple of this value, right? So the frequency multiplies by this n. That's what this wave equation is telling us, right? And in that case, what happens is that if this is C, then this will be C 1 octave higher, 1 octave higher. And then this will be G 1 octave higher. So it's like 1 full octave and then the G note from the C. Okay, 1 octave higher. And then every even multiples, you get the same C, but with this will be C 2 octaves higher. And then the next one will be the E that you talked about. So the one that does 5s, this will be 2 octaves higher than E. Actually, there's a slight flat here, and that's where you get this blue note. It's like people like the blue note. Okay, I see. It's like this note, like it's not the E, but it's like slightly flat. Yeah. That's called a blue note, and the reason we like it is because it's in one of these things. Okay, so that's what you learn about the structure of the sound, and that also tells us why we feel like when you hear a guitar sound, you can distinguish from a drum sound, because drums, if you look at it, look what this is doing, right? When you increase the number k, which corresponds to higher modes, and also n, so you have actually two different numbers for the frequencies. You have the n and k, and you have the very basic 0, 1 mode, and you can have 1, 1, 1, 2, 2, 1, and all these things. And because they rely on the zeros of the Bessel functions, they're actually pretty different. It's not multiples in simple integers like this. So their frequency structure is a lot more complicated. Yeah. And if you actually calculate the ratios between these Bessel functions for different n and k's, you can guess what the frequency structure will be like here. Okay. And these functions, although it's hard to imagine, they actually are different modes of vibration. So for example, you're going to have something like a Mexican hat. Yeah. That there will be a vibration that goes like that, right? And then there will be something that's like bump here and then bump there, and then you might have like two places like this. That's going to be another, and all these are in here. Okay, so. What I'm trying to explain to you is that even though we kind of don't like the fact that we couldn't find the actual A and K or B and K for a specific problem, we still like this result because this result tells us the structure of the sound. And in the early days of music, when digital synthesizers were just coming out, and Yamaha was coming up with their flagship synthesizer called DX7, they were using these sine waves to compose a sound of various things, and they were able to make the sounds of toms by looking at these frequencies and generating them. Okay. So it is kind of awesome that they do, and this can tell you a lot about other things. Like for example, you could ask such a question like, if you hear something, can you determine its shape? That's actually a very famous question. Unfortunately, the answer came out to be negative. There was a mathematician named Katz who questioned, can you hear the shape of a drum? And later mathematicians found out two different drum sets that has the same frequency. But still, I think there's some applications to this by like recording something, and from the pitches you can figure out what kind of shape it would have. Yeah. And let me just go up a little bit further. Now, there are other types of instruments, and another thing is like you have these xylophones, right? Did anyone play xylophone in the orchestra? Okay. Yeah, well, xylophones are, what shapes are xylophones? Rectangles, right? And because they're rectangles, they have also very complicated frequencies. Okay? Except that you have a longitudinal vibration with this other cross-sectional vibration added together. So if you hit a xylophone and if you listen carefully, you'll see that as these things go shorter and shorter, the pitches go up, but there's also this another pitch that's always constant that goes together. And you really need to make this width and the length the right size so that the vibration coming from the width sounds pleasant even with the longitudinal vibration. And so next time when you hear a xylophone, and that's why toy xylophones are terrible. Once you get to these higher ones, then these two things are so close together, they start interfering, and they sound more percussive than instrumental. So next time you get a hands on a xylophone, just try to hear what it sounds like. And for even more complex things like bells, then if you look at bells, then they can vibrate this way or around this way. So there's so many different modes of vibration for something complex like this. So that's why if you hear a bell, it has a much more rich structure, harmonic structure than guitar. Okay. All right. Okay. So in the solution of the wave equation on the disk, I promised that I'm going to show you why the orthogonality relations work. But I want to explain that by bringing us into a bigger framework. And I explained these problem types called Sturm Liouville problems, but didn't really spend time explaining what they are because we haven't seen much before. So now I think we've seen enough examples to talk about these problems called Sturm Liouville problems. And they work like this. If you have d dx px d dx of y minus qx y y, right? And then plus lambda of rx y equals to 0. That's the most general form of the Sturm Liouville. With px positive, rx positive on a to b, and y satisfying boundary conditions, or endpoint conditions, I guess. Endpoint conditions. There are two, alpha 1 y of a minus alpha 2 y prime of a equals to 0, and alpha beta 1 beta 1 y of b plus beta 2 of y prime of b is equal to 0 with alpha 1 squared plus alpha 2 squared bigger than 0, beta 1 squared plus beta 2 squared bigger than 0. Is given. So, suppose this is given. Suppose above is given. Then Sturm Liouville problem is finding all non-trivial solutions and the values of lambda allowing non-trivial solutions. Okay, so that's Sturm Liouville problem. And we know several things about this Sturm Liouville problem. And we actually proved, not proved, but we actually solved such Sturm Liouville problems before, although we did the most trivially easy ones. So the ones that we did was, for example, we had px as 1 and q as 0 and rx as 1. So what was that? That was y double prime plus lambda y equals to 0, right? Yeah. We had alpha 1 beta 1 as 1 and these be 0. In that case, what solutions did we get? We got the signs, right? With 0 and L. Okay. Yeah. So we solved that one, and we also did the other case, same thing, but with these being 0 and this being just negative 1 and positive 1, and then 0 and L. In that case, we got the cosine. Oh, by the way, this is just an easy way to say that at least one of the alpha 1 and alpha 2 are non-zero. Because if they're both 0, then you don't have a condition, right? Yeah. I'm not so sure if alpha 2 has to be positive. Yeah, I'm not so sure. Okay. Yeah, and when we solved it, we call these values of lambda as eigenvalues and the non-trivial solutions as eigenfunctions. Okay? Now, what is Sturm Liouville theory? Well, it knows several things about this. We actually know several things. So let me list them. Number 1, the values of lambda increase to infinity. So lambda 1 is less than lambda 2. So these are all the eigenvalues, okay? So they go like this, and then lambda n increases to infinity. And also, for each lambda k, there is a unique non-trivial solution up to a constant. So what I'm trying to say is that when we say eigenvectors or eigenfunctions, you have a freedom of the coefficient, right? So we just take the coefficient as something that's most convenient to us. But apart from that change, you can only find one per each lambda. Okay. Now there are some variations to this. If you recall, we also had instead of these conditions, we had a periodic condition, right? For the periodic condition, we didn't have a unique one. For each n, we had the cosine n theta and sine n theta. We had two of them. So that's a little different. Okay. But if you're given this, we only have one per each lambda. Okay. Number two, if Qx is non-negative, then lambda k's are non-negative. And that's what I was talking about, that we don't have to search for negative eigenvalues because our case was when Qx was 0. In that case, it's non-negative. So we don't have to take care of that. That's convenient. However, if you have some functions that are negative, then you might have some negative eigenvalues as well. Okay. Oh, by the way, here's something more that this is saying. Eigenvalues are real. And then you might think that's kind of strange because we only work with real valued differential equations. But even if you consider this equation on the complex plane, you can only find eigenvalues that are real. That's the thing. And now number 3, if f of k of x is an eigenfunction with eigenvalue lambda k, and fj of x is with lambda j, right? And if lambda j is different from lambda k, there's the orthogonality relation which says integration from a to b of fkx fjx times rx dx would be 0. Now also notice that if k and j are equal, then again the same story holds. This is squared, so it's positive, and rx is defined to be positive, right? So in that case, you're going to get a non-zero value. Okay? But if they're different, they're in some sense orthogonal to each other. Okay? Let me explain later what that means. Okay? And number 4, and this is a surprising thing, any L2 function. Oh no, I don't want to go there. That's like too much. Right? I'll just say any piecewise continuous function f of x, okay, can be written as f of x equals the sum of k equals to 1 through infinity of ak fkx. Okay. Where the equality holds if fx at points x where fx is continuous. Okay. And just like the Fourier series, if it has a jump discontinuity, then it's going to converge at the half of the jump. Okay. And that actually, you can kind of see why this problem, if you solve it, it's greatly helpful for the PDEs, because that's what we always do. When we solve a PDE by separation of variables, what do? We end up with something like this with one of the variables. We solve it, we get a bunch of functions, right? And then afterwards, when we take those as building blocks and you get a gigantic sum, then there's a problem of representing the initial conditions or boundary conditions or whatever that's given that we didn't care to satisfy as this type of finding the coefficient problem, right? And so this is important. This piece is really important. If we don't have this, this is actually called completeness. Maybe I should write that. Completeness. So what it means is that these functions that come from the eigenfunctions, they act like basis functions for the function space, so that you can represent any function as some of these things. So the specific case we had for the cosine or sine was the Fourier cosine series and Fourier sine series. And then for the disk, we just saw that you can represent any function as sums of Bessel functions, which looked crazy, but it does work. And that's because the Bessel functions, again, solve some kind of a Sturm Liouville problem. Actually, for the Bessel functions, some of the conditions here, it doesn't work. So for example, well, we can, let's not go there. It's just, there's like minor discrepancy with this one, because for the radial function r, you only have the boundary being 0. So r of a is 0, but r of 0, you only have the condition that it has to be finite. Okay. So you really don't have two boundary conditions. You only have one boundary condition being 0, and the beginning part you just have finite. And that still somehow works, because even these conditions are somewhat violated. But nonetheless, it still satisfies similar properties. Now, such an expansion is called, some people just call this Fourier series, a generalized Fourier series, or a better name of this would be called eigenfunction expansion. Yeah, so that's what it is. Now, which ones can I prove? Well, yeah, I can't prove a lot of these. So, for example, I looked at one paper that's like 50 years old that proves this, number 4. And it's actually like, 7-8 page proof. And the idea is that such a differential equation can be transformed into the sine and cosine case, so that asymptotically, when you have a high k value, then it looks more and more like sines and cosine functions. That's like the idea of the proof. And because sine and cosines are complete, you know that that's also complete. That's like the idea of the proof. It's too challenging. This one actually is not hard to prove. I think this is the easiest one to prove. Showing that eigenvalues are real is not hard to prove. Now, why there are unique non-trivial solutions up to a constant, actually I don't know the proof. This one I know how to prove. Okay. So I'll try to do some of these. Okay. All right. So, but before I actually do the proof, you should also know where this problem comes from. So I should start by giving you a different perspective of this problem. So let me do a review of matrix theories. So theorems for matrices. Okay. What do you know from theories of matrices? Okay. So first, we call the eigenvalue eigenfunction, or eigenvector in this case. What's the definition of an eigenvector of A? So you're given a matrix. What's the definition of an eigenvector A? Eigenvector of the matrix A. And then you want to give me the definition of an eigenvector of matrix A.
Suppose the vector is V. Suppose the vector is V.
Okay.
And the corresponding eigenvalue is lambda. It's A V equals to lambda V.
Yeah, that's perfect. Okay, so if the matrix acts on some specific vector as if it was a simple multiplication by a number, then you call that number as the eigenvalue and the eigenvector, this vector as the eigenvector, this non-zero vector as the eigenvector. And supposedly, if you can find, if this is an n by n matrix, and if you can find n linearly independent vectors, eigenvectors, then you can diagonalize this. Okay? Yeah. That brings us to a natural question. Is all matrices diagonalizable? No. Okay.
Not in linear algebra, that right? It says. Oh no, yeah. But in every matrix is upper triangular.
Yeah, you can always make it as upper triangular, but you can't make it diagonal. Okay. So the best you can do is something called Jordan canonical form. How many of you have heard of Jordan canonical form? A little bit maybe. Well, as a math major, everyone should know Jordan canonical form. So definitely take a look what it is. Search it up. Either read in Wikipedia or something. So Jordan canonical form says, well, the best you can get is like you can have some eigenvalues here, A, B, C, D, or something like this. And then in some cases when the eigenvalues are same, you might get a 1 here, which you can't do anything about. Yeah. You might be okay, you might have the zeros, but some cases you might have a 1 there. Or if it's like 3 of them, you might have a 1, 1 here. Okay. That's the best you can do. However, so that's called Jordan canonical form. However, if the matrix is symmetric, then things are different. If the matrix is symmetric, things are different. You can actually diagonalize it if it's symmetric. Okay. So these are called spectral theorems, and if you took the linear algebra course here, then you'll learn them as a complex spectral theorem and real spectral theorem. And it's like this: if A is real matrix, real n by n matrix, and A transpose equals to A, right? Then, meaning, you know what transpose is, right? You flip along the diagonal, so you flip it like this. If it's the same thing as itself, then A is diagonalizable. In R. Okay, so all the vectors will be real, eigenvalues will be real, and you can diagonalize it. Okay? However, in complex, you can do a little bit better. So if A is complex and oh, that's very good. Normal. What's the definition of normal?
Oh, A adjoint times A.
Yeah, A times A
Yeah.
star. So where star means you take the transpose and do complex conjugate. Okay. If this is same as A star A. Yeah. Yeah. This is what normal means. Okay. So a normal matrix is something that satisfies that one. Then A is diagonalizable. Now, even in the complex setting, you can have conjugate symmetry. So it's called Hermitian. So if A is Hermitian, H Hermitian, so that A transpose conjugate is same as A. Okay. If that's true, then A is diagonalizable, and the result is real. So the diagonalized vector would matrix would have real entries. Okay. Now, I mean, you can use. We like diagonalizability because if you learn the basic differential equations course here, then you learned how to take matrix exponentials, right? Like find the fundamental solution. If you have like x, y prime equals to say a 2 by 2 matrix with x, y, then if this is like A, then the fundamental solution is a matrix exponential of this, and it's really hard to calculate this unless you diagonalize it, something like that, right? So in that context, these are pretty interesting questions, and later on, if you're trying to get a job in data science, then things like this becomes important for something called the singular value decomposition or principal component analysis. These are like things that rely on these linear algebra theories, and if you have the basics as a mathematician, then you're in a much better position to know what's going on when you see these things. So that's pretty nice. But now think about what's happening in this context where this is like our inner product. So in all of these, the vector spaces are given explicitly, right? But what if your vector spaces are not given explicitly? It's like some function space, and you don't know what's going on. It's like really complicated. What's going on? Right? So as I said, if you have, so some examples of function spaces are like C1AB. That's like functions that have continuous derivatives on AB. So it's continuous until the boundary, and it's differentiable inside the boundary except for the endpoints, and then the derivatives are continuous, and something like that. Okay. And the reason this is a vector space is because if you to be a vector space, what do you need? You have all kinds of conditions, but most importantly, once you know that you can do scalar multiplication and vector addition, then the thing that you want to check is whether it's closed under addition and closed under scalar multiplication, right? So if you take a continuously differentiable function and multiply it by a number, is it still continuously differentiable? It is, right? Yeah. If you have two functions that are continuously differentiable, add them together, is it still continuously differentiable? Yes. It is, right? So this is indeed a vector space. And there's several others. It gets crazier and crazier. Like this is L2 space, and what these are like functions whose square are finite. So if this happens, then it's in L2. You know that you can see easily that any constant multiple of a function that belongs here should still have a finite integral, so that's okay. What's slightly less trivial is when you have fx plus gx and you square it, is it still finite? And the answer to that is Cauchy-Schwarz inequality for integrals. Okay, you might have seen it in linear algebra course, so that's still true. Now you can also have, oh, by the way, this is slightly better than this one because this one has an inner product, a natural inner product, which is like integrate from a to b of, if you have two functions that belong here, this gives you actually you can do this one if you want to play in the complex domain. So if you do this, then this will satisfy all the properties of the inner product, and you can do that. Okay. So having an inner product means what? You can talk about orthogonal, because if you have two orthogonal vectors, what do you know about the inner product? Or if you don't know what inner product means, think dot product. If you have two orthogonal vectors, what's the dot product? Zero. Okay. So things like this, they act like the dot product. Okay. You can talk about being orthogonal to each other, and that's why these are called orthogonality relations. So here, in this context, it has a weight function. So you can even talk about, I mean, if you stay in real, you don't have to put a bar there, but if you have LAB with some weight function W x, then the functions in here are the ones that are square integrable with respect to the weight. That's finite, and then the inner product in here will be defined as a to b of fx gx times the weight function dx. That's what's going to happen. So in this space, what you would like to know is what's the basis? What's the basis, right? Because if you have the basis, then you can represent all the vectors as the linear combination of those, right? Obviously, these are infinite dimensional. So, like coming up with nice bases that are orthogonal to each other, that would be something that's challenging, right? So how do you do it? That will be like the question that you would want to ask. And what Sturm Liouville does is it changes this question from linear algebra. In linear algebra, you already have a basis, and then you already are given a matrix, and if it's symmetric, then you can diagonalize it, right? However, in Sturm Liouville, it's reversed. You have some inner product, and you have some symmetric operator with respect to this inner product. Okay, so I'm going to explain what that means. And then, in that case, you can try to diagonalize that. And how do you diagonalize a matrix? By finding eigenvectors, right? Now, if it's symmetric, then we can always find bases of eigenvectors. And those become orthogonal. So there's something extra in here. If you have two different eigenvalues, then the corresponding eigenvectors will be orthogonal to each other here. So Sturm Liouville does this. Because function spaces are so much more complex, you change the question. If you have some sort of symmetry, let's find all the eigenvectors, and they will turn out to be bases with real eigenvalues, and you can represent any vector in here by the eigenfunctions. That's how you get the eigenfunction expansion, because this is like linear combination of the basis elements to represent any vector. So that's what's going on, right? Okay, so what I'm going to do is I'm going to actually prove number 3 and also part of one that says eigenvalues are real very abstractly. Okay? Okay, so this is what I'm going to do. Okay, so number 1, I'm going to show that if A of uv is equal to uav, this is called self-adjoint. Being able to move this to the other is called the adjoint of A. And if you can use the same thing, that's called self-adjoint. Okay. Then A, all eigenvalues are real. B, eigenvectors of distinct eigenvalues are orthogonal. Okay, and this inner product, just think of it as dot product. But how do you do dot products? It's like if you have, say, in A2, A3, if you do dot product with B1, B2, B3, how do you compute the dot product again? A1, B1,
plus
A2, B2, or C2, A3, B3. So that if you have A1, A2, A3 with the self, it's going to be A1 squared plus A2 squared plus A3 squared, so that it's the norm of A1, A2, A3, right? That's how you do dot product, right? It's the norm squared, right? Yeah. Now, if you allow complex vectors, so these are complex numbers, then you have to do the bar. Okay. Because then A1 times A1 bar gives you absolute value squared in complex numbers, so that this still works. Okay, so there's a need for a bar. Okay. Now, if you change it like that, and you call this the inner product of A1, A2, A3, and then B1, B2, B3, then this inner product satisfies the following. UV, and if you switch them, VU, then there'll be complex conjugates of each other. Because if you switch them, the bars go into the wrong one. So this actually works. And also, if you have some A times U, it will be linear in the first component. But if you have a number here, AV, then A will come out as an A bar. So that's what's going to happen. So sometimes we call this Hermitian inner product. For the Hermitian inner product, we call this sesquilinear. In the second component, when it comes out, you end up with a bar. So knowing that, let's see. So let me present the solutions first, and then we'll further think about what this condition means when when this inner product is the one that I explained. Okay. All right. So first, proof of A would be, let's say you have AV equals to lambda V. Then AV V is equal to lambda VV is equal to lambda times VV. On the other hand, AVV, now it's self-adjoint, so A can be moved to the other one, right? VAV. And then now AV is lambda V, so V is equal, AV is lambda V. Now what happens to this one, this lambda here?
Lambda bar.
And these two are the same thing, right? We started with the same thing, so those two are equal. And also, furthermore, V is an eigenvector. Eigenvectors are not allowed to be zero vectors, so these can't not be zero. So we can divide both sides, and the result is that we get lambda equals to lambda bar. What does that mean?
That means lambda has to be real.
Yeah. Okay. And then furthermore, B, if you have A of V equals V1 as lambda 1V, 1, and A of V2 equals lambda 2V2, then you can say A V1 times V2 is A V1 is lambda 1 V1 V2, and lambda 1 comes out, so this is lambda 1, and then V1 V2. Okay. And then you can calculate the same thing by moving the A to the other one. And that gives you V1 lambda 2V2. And when this comes out, you get a bar, but we already know that the eigenvalues are real, right? So when it comes out, it just comes out as lambda 2, not as lambda 2 bar. This because, well, it's the same thing. Because this is real, it doesn't matter. Now set these two equal to 0. No, so set these two equal and move it to the one side, and you get lambda 1 minus lambda 2 times V1, V2 equals to 0. Now what does this mean? This means that if lambda 1 and lambda 2 are different, then V1, V2 inner product must be 0. So it's orthogonal. So eigenvectors with different eigenvalues will be orthogonal if this works. Okay, now you might wonder what this condition itself is. So let me explain what this condition is and what it has to do with the linear algebra statements that we made. So one way to think about this is like the inner product that we mentioned, which is A1 B1 bar plus A2 B2 bar plus A3 B3 bar. This is the same thing as saying A1 A2 A3 with B1 B2 B3 with conjugate here, right? Which is same thing as it's like A1 A2 A3 transpose times B1 B2 B3 bar. Okay? Now, under this inner product, let's see what this condition is saying. It's saying that if you have AU transpose V bar, that's this inner product, right? So inner product is this times, we're thinking of all the vectors as column vectors, okay? So we have column vectors, and then you multiply them, and then the second one has a bar, right? Okay, and then this one would be U transpose times AV bar. Now, do you know how transpose X to matrix multiplication?
So it's U transpose.
It's U transpose A transpose V bar. Okay, so they switch when you do the transpose, okay? And then if they are equal, then you see that AT and A bar should be the same because all the other parts agree, right? So if these two have to be equal for all vectors U and V, then you have no choice but to say AT is the same as A bar. But what's that? You can take bar both sides, so you can do this. That's called Hermitian matrix. Okay, so self-adjoint matrix is under this inner product is the Hermitian matrix. And that's why if you use the standard inner product or the dot product with the bar on the second one, then all the properties that I listed would work. So these matrices are diagonalizable with eigenvectors and eigenvectors of different eigenvalues will be orthogonal, and also all the eigenvalues of this will be real. That's what we know. Okay. All right. Okay. So so we have those two theorems for any vector space with inner product, and A being self-adjoint. But I still haven't shown why this is going to create this. Okay. So in order to show that, what I have to do is, all I have to show now is that I have to show that this one is somehow related to a self-adjoint operator. And if that's self-adjoint, then you're done. If it's self-adjoint, if there's some operator here that's self-adjoint, then all the statements I made about the general self-adjoint maps is going to work. Okay? So here's how you look at it. So remember that we want to think of this as AV equals to lambda V, where V's are the solutions here. And it doesn't quite look like that because there's an Rx in front of lambda, right? So in order to make this work, what we have to do is we have to first move this to the other side and divide it by negative R. So it's going to be looking like this. It'll be negative 1 over Rx ddx px ddx y plus qx over Rx y equals to lambda y. Now it still doesn't look like A times y equals to lambda y, so I'm going to rewrite the left side as an operator form. So in operator form, this is how it looks like. It's 1 over Rx. Let me just rewrite this as dx, and then px dx plus qx over Rx applied to y equals to lambda y. Okay. Now if you do this, then you see that this left side is an operator, and we are really, the Sturm Liouville problem is really, what is it trying to do? It's trying to find the eigenvalues of this eigenfunction equation. That's what we're doing. Okay? All right. So what do we have to check?
Self-adjoint operator.
We have to show that this is self-adjoint operator under the following inner product. So if I define fx gx as this weighted inner product, then I have to show that if I call this operator as L, or let me use a different color. If I call this operator right here as L, then LFG should be shown to be equal to FLG. Okay, and then we're done. Oh, by the way, there's still something that I'm not doing correctly because it's there's a bar somewhere to make it fully workable, but it's okay. One thing is I might mess up, and it's not a big deal. You can, if I mess up, you can just figure. I mean, if you mess up, you can just figure out where you should go. Okay, so I'll just leave it like this and then try to show self-adjointness. Okay, and then if it's self-adjoint, then immediately this is true. Number 3, and being real eigenvalues, that's true. Okay, this is really hard to prove. I can show you this, but I don't think we have the time. This is not that hard, so maybe I can try to show it tomorrow. Okay. So now let's try to show what's going on. So here's what we do. So if I do L of fx gx, and eventually what I want to do is I want to do this bunch of calculation. At the end, I want to show that that's same as fx L gx. Okay. If that's done, everything follows. Okay. Yeah. So let's try that. It's kind of ugly, so I'm sorry about that. So we do integral from a to b of -1 over rx dx px dx. Let's put the f here. Okay, and then plus qx over rx fx times gx rx dx. Okay. Immediately you see that, what do you want to do? The first thing you want to do is
bracket.
right? Get rid of the rx. That's the most annoying part, right? Let's get rid of that, and then think about what this is. This is like f is differentiated once, and you multiply by p, and you differentiate once. Okay, so this is what you get. You end up with 2 integrals. One is a to b of minus px times fx, f prime of x and then prime. Is that good? Dx hitting f of x means you differentiate once, and then you multiply by px, and the entire thing is differentiated. Okay. This r is gone. Okay. And then times gx dx. That's one integral, and then this times this is another one. Okay. So you have plus a to b of qx fx gx dx. Okay. Now if you look at this, you kind of already see that this is okay, because you can think of qx not to be multiplied to fx, but multiplied to gx, right? You can think of this as multiplied to here instead. So, oh, by the way, I said I don't worry about this bar. It all works because these are real value functions. So whether you put the bar there or not, it doesn't matter. Okay, so qx can go here, so that's not a problem. But here, I somehow have to move the prime and the multiplication and the prime over to g. I have to move these to the other side. What allows you to do that? How can you move the derivative of one side to the other one?
By parts.
Integration by parts. Okay. Yeah. It will be our favorite method. Okay. Once you go to analysis, you can't really do much other than integration by parts. It's all integration by parts. Anything that sounds really fantastic is really just integration by parts. Okay. So integration by parts says you integrate one of them. Okay, so I know you guys like the Okay, so I did the tabular, and it doesn't work really well in these settings. I know you like the UdV equals to UV minus VdU. But even this, I don't like. The one that I really like is this form, and I don't know why people don't write it like this. If you have two functions multiplied, this is saying that you integrate one of them. So capital G of x is like antiderivative. Okay? So you integrate one of them, minus you differentiate the one that you didn't integrate. This is equivalent to this one. Okay? Can you see that that's indeed the same case? And if you do it like this, then it's easier to see what you're doing without having to choose which one's dv, which one's u. This is just too much. Okay? So let's just do it that way. Right? So what I'm going to do is I'm going to integrate this one, but later differentiate this one. Okay? So here's what I do. If you integrate this, it'll be negative px f prime of x gx, and you plug in b and a, and then because there's a minus, it will now be plus, and you have a to b of the one that's already integrated you keep, but the one that you didn't do anything to, that's going to be differentiated. And for this second one, let's just move the q to the other side. Okay? Okay. Sorry, I'm going a little bit over time today because I had to spend a lot of time with other stuff. Okay, so for this one, if you plug in P of A, f prime of A, G of, sorry, yeah, A. Okay, well, this one, so actually this requires a little bit more thinking because you remember the boundary conditions when we had like y of alpha 1, y of A minus alpha 2 of y prime of A should be 0. The special cases were when this is a 0, this one is 0. So actually with these general conditions, you can show that this is 0, but let's not go that far. Just look at this one. If it's the value of the function at A is 0, then this will be 0, right, because of GA. And this will be 0 because of GB. Right? If the condition was that only the derivative is equal to 0, then this will be 0 and this will be 0. Okay? And then what happens if you have a mixture of both? These are called Robin conditions. And if you have Robin conditions, then you can actually multiply something to the top and multiply something to the bottom and subtract or something, then you can get that this is 0. Okay? So sorry for being so less specific, but what happens in here is that this is going to be 0. They're both going to be 0. So in general, these two cancel each other for general conditions. Okay? Special conditions, these are individually 0. Okay? All right, so now what we're going to do is, now we're going to move the px to this one, g prime of x, and then now I'm going to integrate f prime. So let's see what happens. If you do that, then it's the integral will be f. What's the integral of f prime? It'll be fx, right? Px g prime of x. Again, you plug in the boundary points, okay, and then minus. See, now these are the ones that we didn't do anything to, and these together will have to be differentiated. So what happens is that the one that you integrated, you don't do anything to it, but then the one that you didn't do anything to it has to be differentiated. Okay, we still have that one, plus integral of fx qx, and I'm going to put over rx, and then gx, and multiply by rx dx, just to get ready for the other side. Okay. Now, again, for the same reason, this is going to be 0. And look at what happened here. Isn't this exactly like this one? With a minus, right? So all you have to do now is just put 1 over Rx and put Rx here. So let me write it in black. It's going to be confusing. So you can put over here 1 over Rx. You can put here times Rx. And then if you factor the f of x out, here's the end result. We get integral from a to b of f of x times negative 1 over r of x dx px dx of gx plus qx over rx gx times rx dx, which is exactly FLG. So we're done. Okay, so we just show that this operator that's involved in the Sturm Liouville is self-adjoint, and because it's self-adjoint, all the eigenvalues are real, and the eigenvectors, eigenfunctions of different ones will be there. Yeah. So just one more. Sorry. What does this have to do with the Bessel case? Well, in the Bessel case, remember what the formula was. It was a r squared r double prime plus r prime plus lambda r minus lambda r squared n squared y equals to 0. So that was the this was the thing, and this one is actually this is like r double prime, no, r prime times r. Right. So if I divide by r squared to everything, this will be 1 over r minus n squared over r squared y equals to, actually this will be plus, this will be minus lambda y. Okay, so that's the form, right? So because of this one here, the integral between the Bessel functions will be Jn k over a r. So these were the eigenfunctions, right? So Jn m a r, and then because this is the 1 over r function, so that's just simply r, and you integrate r from a to 0 to a. That 0 to a. That's why this is equal to 0. So earlier on, I explained that this is equal to 0, and I actually proved that for free from the Sturm Liouville. Okay. All right. Thank you for bearing with me.